Hello, everyone. Can you hear me all right?
Yes.
Let's get going. Hello, everyone. A year ago at this very summit, we launched the Water Innovation Hub to accelerate the commercialization and deployment of water technologies, a space where we saw a real gap and immense opportunity. So 12 months in, I'm excited to share what we're building, what we've learned, and where we're going. I'm Aishwarya Kurutukulam. I'm a director at ClimateHaven, and I've had the pleasure of leading this initiative over the last year. So water, it is pretty unique. It's an essential ingredient to our economy, but at the same time, we feel the worst impacts of climate change through water. Droughts, floods, hurricanes, extreme weather events. This graph, for example, shows the number of billion-dollar disasters in the US over time. And it's happening, right? It's getting worse. And at the same time, water underpins our economy. We use around 321 billion gallons of water each day. And that's for industries like energy, irrigation, all essential to our economy. And as chips, semiconductors, AI, and the new emerging economy grows, this demand increases. So the circumstances are changing. The need is really here. So there is a real innovation gap in water. At ClimateHaven, we work with founders every day, whether you're spinning out a novel membrane technology from a Yale lab, or you're finishing your first pilot with a potential customer. We've really become extensions of student teams. And what we've also noticed is the other gap of founders building solutions without a clear understanding of customer problems. And on the other side, industries and corporates don't know exactly how to engage with the startup community. So that's exactly what the hub is designed to build. We accelerate early stage innovation to real world deployment by providing pilot pathways for startups and for customers, really being able to identify where startups can move the needle. I should have clicked through that. So the main three pillars that we have based our hub on is one, to accelerate breakthrough technologies through research and incubation, to validate those in the real world through pilots and commercialization pathways, and drive the sectoral transformation through insights and partnerships. So over the last year, we've launched our first Pilot Innovation Challenge with our wonderful founding partner, the Regional Water Authority. You'll hear from them in just a moment. With them, we offered nucleic sensing systems $30,000 to pilot their environmental DNA sensor technology. So this technology can detect harmful algal blooms and potentially could save the utility tens of thousands of dollars each year in operational costs. Beyond that, we've been getting smart on water, trying to understand what startups truly need, what corporates really looking for. And that's been through putting out insight pieces, doing market landscape reports, hosting a wonderful workshop series with the Yale Center for Business Environment, and also a sold-out event at New York Climate Week, the first one, and we're back this year again, where we brought together industry leaders, investors, innovators, and more. And none of this would have been possible without the right partners. Our founding partner, RWA, has been extraordinary. It's really unique for Utility to be this forward-thinking and to come into the conversation really wanting to pilot and support startups. And that momentum has brought on our other big corporate partner, Xylem. They are a global water technology leader, as you may all know, and they are providing access to their infrastructure and deep technical knowledge, really recognizing the urgency and possibilities for early stage innovation in water. And what we're all here for today, the wonderful faculty at Yale and UConn, and we're going to be hearing about the emerging research that's coming out of the labs. But beyond that, these institutions have built centers that are supporting entrepreneurs at the early stage. We're excited to partner with the Yale Water Innovation Center and the Connecticut Center for Applied Separations Technologies, both providing analytical and testing equipment that is necessary for startups at the early stage. And beyond the early stage, you also need to integrate these systems into utility and corporate infrastructure. And that's what Continua, our technical partner, brings in. So I am very excited to announce our next innovation challenge with Xylem. So we have identified two really interesting themes. One, recovering critical minerals from wastewater sources, including produced water, acid mine drainage, desalination, brine, and more. And the second, in energy recovery from water-intensive industrial operations. So these are real opportunities with real customers and open to any startup around the world who's really solving for these issues. So with that, I know that's getting a lot in the last 5 minutes. With that, I'd like to pass it on over to our founding partner, the Regional Water Authority. We will have Victor Benny, who's the head of engineering, and we also have Jim Hill, who's the head of operations here today. Victor will be speaking first, and then we'll be hearing from Professor Jae-Hong Kim, who is leading the Yale Water Innovation Center. Following that, we will have faculty presentations, which is the part I'm looking forward to the most. So thank you.
Thank you, Aish, for the wonderful introduction. I guess you're all lucky enough, if I had known there were 3 screens, I might have made the effort for a presentation, but you're all lucky enough to catch me, or maybe I'm lucky enough to catch you folks right before the lunch coma kicks in. So keep on eating, enjoy your lunch. But good afternoon, and again, thanks, Aish, for the introduction. So water is life. It's the lifeblood of our communities, our economy, and our environment. But today our relationship with water is facing unprecedented challenges, from aging infrastructure and climate change to the need for continued conservation. The water sector is at a critical crossroads. Solving these challenges won't be easy, and no single organization can do it alone, and that's why we're here today. At the Regional Water Authority, our mission has always been to make life better for people by providing high-quality, reliable water and services, and acting as responsible stewards for the environment. For decades, we've protected thousands of acres of our watershed area and operated state-of-the-art treatment facilities to serve hundreds of thousands of people in the greater New Haven area. But to protect our water future for the next generation, we must do more than the status quo. And that is exactly what the water innovation is. It's the shift from the lab to the real world. Emerging technologies like real-time sensors for water quality, autonomous inspection robots, and advanced leak detection are just the tip of the iceberg. Yet taking these breakthrough ideas and translating them into practical, scalable solutions is not easy. Innovators often lack the data, testing grounds, and operational expertise needed to prove their concepts. Water technologies like the RWA, on the other hand, need these modern technologies to combat the escalating pressures on what is our aging infrastructure. To bridge this gap, we collaborated with ClimateHaven and launched the Water Innovation Hub. The founding of the Water Innovation Hub is a testament to the power of targeted cross-sector collaboration. By teaming up with ClimateHaven, we are breaking down silos. Through structured pilot programs, we are granting startups direct access to RWA's infrastructure, operational data, and industry experts. For example, initiatives like the annual Innovation Challenge transcend typical pitch competitions by equipping startups with non-dilutive grants, funded pilot programs, and the practical testing environments required to validate their technologies in the field. A case in point, we look at what we're doing in our West River watershed. We're partnering with Nucleic Sensing Systems, also known as NS2, to pilot groundbreaking genetic screening technology. Think of NS2's system as an early warning genetic smoke alarm. It sniffs out the molecular signs of toxic algae long before standard lab tests can give us proper results. This gives us time to adapt to these blooms, sometimes before they even start. Innovation also requires fresh perspective and next generation talent. That is why we're collaborating with students through the Corporate Water Risk Workshop. By bringing bright young minds together to analyze modern climate and corporate vulnerabilities, we are cultivating the future leaders of the blue economy right here in New Haven. All of this collaboration transforms the RWA from a traditional utility into a living laboratory of sorts. We are empowering next generation of water tech entrepreneurs to test, refine, and deploy their solutions right here in Connecticut. The results, we accelerate the commercialization of technologies that will enhance water quality, system resilience, and environmental stewardship, not just for our customers, but for the broader U.S. water landscape. The Water Innovation Hub proves that when you combine the ingenuity of entrepreneurs, the backing of visionary corporate and municipal partners, and the resources of our local innovation system, we can overcome the defining climate and infrastructure challenges of our times. New Haven is rapidly emerging as the center of gravity in the water industry. Together, through collaboration, innovation, and shared commitment to a sustainable future, we are ensuring that whenever you turn on your tap, the future of water is smarter, cleaner, and more resilient than ever before. So I want to thank everybody for taking part today and actually congratulate you. You're all hopefully going to become part of this solution of leading us to a more blue environment. And I like to think of it as, taking things one step at a time, or in this case, one drop of water at a time. So thank you.
Thanks so much. Next up, we have Professor Jae-Hong Kim, who will introduce the Yale Water Innovation Center, and we will also quickly transition to hearing about Professor Kim's research at his lab, and that will be an 8-minute presentation followed by 4 minutes of Q&A. So have your questions ready, and I'm sure you want to really understand the awesome research that's happening here.
Hello, I'm Jae-Hong Kim. We have Water Innovation Hub to accelerate the commercialization and deployment of water technologies. The logical counterpart at Yale is where those technologies are born, and that's what Water Innovation Center is about. We've been working on this center for past a couple of years to launch. We haven't launched yet, and this is actually the first public presentation to share Water Innovation Center to the public. For past 2 to 3 years, we've been working with Yale Engineering. Here we have a Deputy Dean Sarah Miller here. For the same reason, we have a lot of amazing research in water technologies, and we now have an amazing partner on our Innovation Hub. So this is the perfect time for us to really present this to you all. I also am here with Professor John Fortner, Professor Lou Raskin, who've been going to be the Deputy Director for the Water Center. And we have 12 other faculty members who are members of the center, ranging from engineering to School of Environment, Public Health, Architecture, and Chemistry. So we do have a large number of expertise ranging in many different disciplines who are contributing to the birth of water technologies that is going to be nurtured later by Water Innovation Hub and all of you. So I will just spend a few minutes to describe what center is about. We have 3 pillars. The first pillar is the core service. What that means is that we have state-of-art instrumentation. We provide service for the method development and training of the people. And also, if you are industry and utility, we do service analysis. So we do have, this is a set of equipment. We have more to come. Again, this is just like university core or external laboratories that you, as you may say, that where you do state-of-art analysis of the water quality. Compared to some other technologies in IT, water technologies has to have very strong support for the quality, measurement, and that's somewhat unique. And I think this is going to be a key infrastructure for continued collaboration with the industry along this hub. Another 2 pillars are research and innovation and a professional master's degree program. I'm presenting these 2. These are pretty well tied to each other. We, all the faculty, like to do research. So we are going to have some internal research grant that we can work on new ideas and new technologies. But then we are going to make it a strong connection to the education of the student, and also a professional master's degree program that we are going to about to launch, such that the research that we do within the Water Innovation Center not only addresses emerging subject, but at the same time really connects to the industry who are part of the hub and part of the center, including performing a research demanded by the industry and utility partners, as well as promoting internship with industry partners. So I have a small diagram about the research that we do. Water Innovation Center, we call it Y Week. Professors like me, we always tend to work on this little subject that not many people care about, super excited about, fundamental science, out of intellectual curiosity, writing a paper. And if we are given opportunity, we are going to continue to do that. And that's exactly what we are going to continue to do. But at the same time, for Water Innovation Center, what we are trying to really hope is to promote the research and development toward the direction of commercialization and deployment. And our outcome, the water center's deliverable in many years to come, I would say is going to be IP and startup. Within Yale, we have a tremendous resources and infrastructure to promote commercialization effort and entrepreneurship. To name a few, Science City, Roberts Innovation Fund, Planetary Solutions, CEID, Yale Ventures. I'm sure you have heard about this as you spend some time at Yale. And we are now partnering with industry partners and utilities, you all down the road, State of Connecticut, and CCAST by Jeff McCutcheon, who is going to present after me, and of course, Water Innovation Hub. And as you can see, there is this connection at the top, Water Innovation Center and the industry partners. As I said, it's not only about the research, but at the same time, education. So partnership through research and education is something that we are looking for to establish. All right, so we already have the center, which is about 3-minute walk from this location. As you might have heard, Yale is expanding significantly. We are moving into a new space in about 4-year brand new building, brand new water center. But this is our temporary laboratory space. We already have a website. We are going to officially launch through Yale News sometime late summer or early fall. Until then, you're welcome to contact me. My email address is there. We already have a website. Please take a look, and I'll be happy to follow up with you who are interested in this effort. Thank you so much. Yeah, so before I go to the research, are there any questions about the Water Innovation Center? We call it Y Week. Yes, Amanda.
I have a question from the industry side. I think this is really interesting. So what is your process or perceived process for bringing in industry and working with them? I see where there's opportunities, but what is the actual solid pathway of engaging?
Yes, we are working on having an official membership with industries partners. The membership will include our access to our IPs and annual meetings and access to our instrumentation, as well as the access to our student interns. So, but we haven't finalized it, and that's the reason why it's taking a little longer time. So we should be able to share all the details by the time that we officially launch. Yeah, but we would love to. Working with the industry is extremely important, especially for this particular effort, because that's the goal of this center. Okay. Well, we can talk more about it later. Before I jump onto my research, now we have Professor Fortner and Raskin who is going to talk about their research, but I wanted to just present a couple more, our key faculty in environmental engineering who wanted to share their slides so that you can take a picture. I'm not going to spend all the time describing all this. This is too much. Professor David Quabi joined about 3 years ago, and he is working on this redox flow batteries for energy, but at the same time, he's doing a lot of electrochemical process for the resource recovery. So please take a picture or at least, write down name and you can later study this researcher. Another younger faculty, Professor Leah Winter, she joined also a few years ago. She is working on electrified processes, electrified membrane for nitrate reduction and other water pollutant abatement, as well as she works on this low energy, low temperature plasma system for water treatment and resource recovery. So I hope you remember these names and later get connected to our superstar young faculty members. So I'm going to spend next 2 hours, right? To talk about my research. I have a long list. I have a wide range of interests because, you never know which one will get funded. But anyhow, I'm going to skip a few slides. I realized that I don't want to spend too much time. So most recent research on hydrogen peroxide synthesis, you heard about hydrogen peroxide as an alternative liquid fuel, but my interest in water treatment is to produce hydrogen peroxide on site by reducing oxygen, just using electricity, not in an idealized solution, but real groundwater, real wastewater. Why do we want to do that? Because we want to produce hydrogen peroxide and use that hydrogen peroxide, activate it, and then destroy pollutant. We call it advanced oxidation. And when you are doing advanced oxidation, not in a huge scale, but more smaller distributed scale, I imagine that this is going to be one of the key technologies that we can explore down the road. So this is one of our recent work. Related to that is that this is a catalytic membrane system. So what it does is that it activates hydrogen peroxide or other precursors such as persulfate. They produce radical, and then these radical go and destroy pollutants. Well, so this has been pretty successful in lab scale, and we then got really excited. And a couple of years ago, we started a company called Catala. And some of you may have heard a company called Catala from this Water Innovation Summit. We are recently folding it, and Claire Schunar sitting there is a co-CEO. So after this, you can ask her why we failed. But I don't necessarily say that as a failure. It was an amazing experience, at least for me and for my student, to go through starting a company, and we are not able to, get a large investment to continue. We learned a lot, and we are now looking for the next opportunity. So, from educational point of view, it's never a failure. So, I would be happy to continue this process down the road. This is another example of the membrane. This is an electrified membrane, just like Professor Winter's research. So our group has been making different type of material, and then this modular system goes and destroy pollutants or used for resource recovery. Keep talking about a similar concept here. Now we have a hydrogen peroxide synthesis cell, and this is an electrified system. The way we are imagining is this is for household application. So this is a very confined, small system that just uses electricity. It produces hydrogen peroxide, and it activates hydrogen peroxide and destroy pollutants in a very small system using iron in the natural water as a precursor chemical. I'm not going to go through details, but again, this is sort of a small household system that we see. We hope that there's a commercialization path downward. One of the research bottleneck that we have, how much time do I have, Aish? 4 hours? Okay, fine. All right, so we have been working on electrochemical cell. And one of the, you might have noticed that research that we do in academia, one of the bottleneck is longevity of the system, not to mention the cost. So a lot of new technologies, does it really last in the field on a long run? And that's something that we've been working on. And this is an electrochemical system that destroy pollutant called 1,4-dioxane. And this is the system that is stable for a really long period, which is a big contrast to some of the technologies that we have studied in the past. This is not really ready for any commercialization, but I thought you might like this idea. You have a small faucet filters in your home, right? And then after use, you throw it away, but you never know whether it is ready, it's dirty. They say after about 6 months, you have to change it, but you never know it is saturated. And you don't know how to regenerate it. So this is a new type of system, absorbent, that catches the pollutant. And then what you need to do is to send the warm water. The material changes the conformation and releases the pollutant so that you can use it again. So basically, the idea of treating home filters using warm water sounds simple. It is not ready, but I'll be happy to study more. Somewhat similar is that now you have a home filter and you probably saw that the little red light that tells you then you need to change the filter. It has nothing to do with how the filter is performing. After some period, it just gives the signal. There's currently no technology that tells you when the filter is dirty enough so that it needs to be changed. So we are thinking about this canary sensor. You probably heard about canary in the coal mines. When it goes in, canary stops singing. There's something wrong. You gotta evacuate. So we are making this canary right there, that small little thing that goes into the filter. At some point, it gives a signal, hey, user, do not drink this water more because the filter is saturated. So that's something that we've been working on. And this is one of the subjects that we are working on thanks to Rover's Innovation Fund at this moment. I also wanted to introduce this research. You probably heard about this ultra pure water, the new silicon for era of computing. Some people say ultra pure water is becoming a significant bottleneck as we are building many more chip manufacturing facilities around the world, and it tends to be in regions where the water resources are being competed with human consumption and other agricultural use. And so one of the research that we are doing now is to significantly enhance the efficiency of a UV-based system, because one of the bottlenecks in semiconductor chip manufacturing is its capability to destroy some of the pollutants that are prevalent especially in water reuse scenarios. And this has been, again, in serious bottleneck in expansion of the chip capacities of the world. All right, so I'm going to finish my presentation by showing my research group members. But anyhow, I'll be happy to discuss a little bit more. I went through a little bit too shallow, but I didn't want to spend the next 2 hours digging into the details. But I'll be happy to entertain any questions. Thank you.
I always have questions, Jaehan. Very, very amazing work. With this advanced oxidation processes that you're integrating into electrified membranes, what have you detected in terms of byproduct formation? Is a concern with complex aqueous mixtures?
Right. So especially when you have a chloride, the chloride formation becomes a concern. But depending on how you operate it, actually, one of the systems that we are doing for direct electrode station, so we have this set of electrode, porous flow-through electrode, and we are doing current alternation, so pulsing. And one of the benefits of pulsing is to protect the electrode, but also it prevents the oxidation of species all the way down to perchlorate, for example. So that was one of the unexpected benefit of some designs that we are doing to lengthen the cell life. So that's one example. But I'll be happy to talk more about it. Yes.
So there's a big sort of gap between where municipal water tests occurs and then the tap at home. And I'm curious, how you think families, households ought to be protecting themselves or testing their water effectively.
So, quite a large number of people are relying on water that is not provided by the municipality, and a large number of people are actually unprotected. And that's the reason why there's a lot of research on Superfund site where we want to understand what's in the water and what are the solutions. Are we going to send all these advanced treatment technologies to every homes that are relying on groundwater well? That doesn't sound right, but there should be some cost-effective solutions. And one of the, whenever you want to try, you want to destroy something, you need an energy. And the energy can come from chemicals, and that's what you do when you pour chlorine into the water, or sometimes it can be electricity. And as you know, electricity is a much more sustainable and reliable option, and that's the reason why a lot of research is now gearing toward how we provide sort of simple solution to the various pollutants using electrified systems. I sometimes feel like, down the road in 10, 20 years, you go to Home Depot and Lowe's, and there must be very simple, modular systems where, depending on your water quality, you can just, connect and address to your water needs. Even though you are in this region, some areas have more 1,4-dioxane, some areas have more iron. It's extremely heterogeneous. How do you approach that down the road for the future is a very tricky question, but at least I think, the technological innovations will certainly address some of these challenges down the road.
You're working on a great range of technologies, basic research. I'm curious how you think about commercialization of work in your lab. If you think about it at all, were you leaning on the new YWIC to do that, or how are you thinking about that?
Yeah, so that's a really good question. I was not thinking at all a few years ago. I was more of a fundamental scientist that I would love to write a paper, et cetera, but Yale Engineering Water Innovation, this Innovation Summit, these are all relatively new, and there's a huge driving force from university to think, hey, faculty, it's great that you're writing a great paper, but why don't you think about this? That actually gave a motivation more. So that's the first. Second, we have a student who get more and more exposed to this type of event. They come and they start to think about this entrepreneurship, and that is a driver for the faculty, to be honest. I don't want to start a company. I don't have a capability to start a company. It really depends on students like Claire, who has the vision, who wants to learn, who wants to, expand her capability. And she and I work to start a company. So all these things, like, these new changes, are contributing, helping us to rethink our job description.
Thank you. As you can tell, we have an awesome partner at Yale with Professor Kim and all the wonderful faculty at Yale. As you can see, there's a wonderful range of innovative projects, and often we are approached by students asking, what kind of work should we be doing, which kind of industry? And the key part and the reason why we're having this session is to kind of really bridge that gap. So I would urge you to think about, as you look at each of these technology areas, like what is the potential application, what is the industry application, and how do we bridge that? So yeah, with that, I would like to now invite Professor Jeffrey McCutcheon, who will do a quick introduction on the Center for Applied Separations Technologies, and then transition into his research work.
Thank you, Aish. It's great to be here and be part of this conversation. I actually was here 18 years ago on the steps of Mason Labs when I graduated with my PhD from Yale Chemical. It was Yale Chemical Engineering back then, now Chemical and Environmental Engineering today. And
it was here before I actually went up the road to UConn where I got my love of water technology and understood some of the interesting challenges that we faced. At UConn, I've created a center called the Connecticut Center for Applied Separations Technology, which is devoted to developing new technologies around membranes to enhance our industrial processing of gases, liquids, and ion-containing materials. And so we offer a whole suite of services ranging from piloting to manufacturing to characterization of membranes in a variety of industrial processes. And this has been a very exciting thing for us to work in because we can basically do a lot of the applied work that I think some people in this room might be interested in. And we do this through a variety of activities. We have an annual industrial separations workshop, which I'll talk about in a few minutes. We have a lot of student engagement, lots of award-winning students in training in membrane technology. And we have world-class customized equipment that we built ourselves for testing and evaluating new membrane separations technology. And when I went to UConn, I didn't really expect to move in this direction of applied research, but then I began to see what UConn offered as its own living laboratory. Some of you may not know, but UConn owns and operates its own wastewater treatment plant, conventional wastewater treatment plant that treats all of its water plus the surrounding community. This plant actually feeds a state-of-the-art wastewater reuse facility. Yeah, we do wastewater reuse in Connecticut, a place that gets 50 inches of rain a year. But this reused wastewater is used at our power plant, which is the largest water user on campus. And when we installed this wastewater reuse facility, it lowered our campus water use by 20%. The UConn utility plant, which creates heated steam, cooling water, and electricity, 25 megawatts, was built and saves UConn $10 million a year, your tax dollars, that help us to operate more efficiently and cost effectively with a lower carbon footprint and reduced NOx emissions. And we even have this little-known operation down at Groton, at one of our regional campuses, the Rankin Laboratory, a seawater intake facility focused mostly on marine biology. But if you have a desalination process you want to pilot or test, you have a southern-facing sky for solar and direct access to a filtered seawater feed. We also offer the Center for Environmental Sciences and Engineering, a full-service analytical laboratory that can evaluate metals, nutrients, organics, and emerging contaminants with state-of-the-art equipment. And this infrastructure and this mission have merged to make UConn a very sustainable campus. And we're dedicated to sustainability in many different ways. We've reduced our greenhouse gas emissions by 20% since 2007, oddly enough, about the year before I started. And then we also reclaim almost 500,000 gallons of water per day from our wastewater systems. We reduce our trash by 23%, and have a number of sustainability-focused courses at UConn. This has led us to becoming one of the Sierra Club's cool schools. Have you heard of this ranking? It's a really cool ranking that evaluates a university's commitment to sustainability from its educational and other activities. I'd be remiss to say that Yale's also on this list, a little farther down. But I know how Yale is really interested in its national rankings, and so this partnership will actually raise up our Connecticut average a little bit. So I'm very excited about this. No, I only kid. Yale's commitment to sustainability is incredible, and I think we just saw why that is from some of the research being done here. So I'll just briefly talk about some example of water technology innovative projects that are happening at UConn, and I'm collaborating on these projects. These are going to be high-level overviews, kind of like what Jae Hong just talked about in his lab. The first I'll talk about is a new technology that we have created at UConn around customized membranes for water treatment, based on a new manufacturing technology that I just pitched about across the street at the climate pitch session. This is a technology platform that uses electrospray to customize membrane chemistries for specific application spaces. Water treatment today is much more complicated than it was, say, 50 years ago, because now we're trying to reuse water, we're trying to treat different kinds of water, and we're trying to treat water to different levels of treatment, so fit-for-purpose water. For that, you need a specific membrane, and the commercial sector does not offer such membranes right now. They're a commoditized, limited offering industry. This technology, though, has applications beyond just membranes for treatment. We've also developed sensor technologies for water monitoring. So with Baikun Lee, one of my close collaborators in environmental engineering at UConn, we've developed selective ion, selective membrane, or solid-state ion selective membrane sensors with electrospray technology for the monitoring of ammonium in wastewater. And we can add to this many other metals that we might want to monitor in wastewater systems. And these are more robust. They have a faster response for a variety of reasons, and they have excellent longevity. We also work in the area of anaerobic digestion, and this is sort of getting to the idea of a circular economy around water and wastewater, where we can recover value from our wastewater. Anaerobic digestion is a ubiquitous technology in wastewater systems today where we can generate biogas, which can be burned for energy and combined heat and power systems. And what we've done is been funded by the Department of Energy to develop a digital framework for optimizing anaerobic digestion performance by actually inserting these sensors that I just talked about into an active digester up at Greater Lawrence Sanitary District. And that has enabled us to build better models to predict how digesters will perform with different feedstocks and to assess those life cycle benefits for recovering value from wastewater. This has ultimately led to a recently funded RPE project on recovering valuable nutrients from wastewater, most notably ammonia and phosphorus, using a combined membrane distillation and ion exchange membrane system. The membrane distillation captures gaseous ammonia, and then ion exchange can capture phosphate as phosphoric acid with bipolar membrane electrodialysis. That membrane for the phosphate recovery is built with our electrospray-based process, and we are collaborating with Baikun Lee, George Bolus, and a number of companies that are supporting this effort. And then we're also trying to reduce greenhouse gas emissions from wastewater treatment systems, led by Baikun Lee with another Department of Energy funded grant. We've built pilot-scale biological nutrient recovery removal systems, which are allowing us to measure N2O emissions from wastewater treatment and then to apply those to UConn's actual wastewater treatment plant with a high-fidelity sensor network so that we can better operate that plant, optimize aeration and other processing parameters to reduce greenhouse gas emissions and reduce energy costs. We mentioned commercialization. I think that was asked to Jae Hong as well. This is something that UConn is passionate about and that I'm passionate about too. This electrospray-based technology that's touched many of our projects that I've talked about today has led to the spin-out of MembraneX, a company that's accelerating membrane development for water treatment and other separation technologies, because we can demonstrate scale-up of the process, and this award-winning technology hopefully will see some commercial success. I'd also like to announce the Industrial Workshop on Separations Technology. This is an event that happens every fall up at the Innovation Partnerships Building at the University of Connecticut. This year's will be on October 2nd, and we bring in typically 10 to 15 industrial speakers, another 15 panelists from industry, so you don't have to listen to any academics, which is kind of nice sometimes, and a startup pitch competition and an early career workshop for students that are in the room that want to attend. But I hope to see you there. If you would like to get an invitation for this free workshop sponsored by the Department of Economic and Community Development, please give me your card before I leave today. And I'd like to just thank you all for listening. Go visit our website if you want to see more of our work. We have a great group, a great team of collaborators, and great funders, so thank you very much.
I was a question about commercialization. So I saw a couple of companies on there, like Nala membranes, for example, that was maybe it was a product of your lab, and if you could talk about that, how they emerged, or what the partnership might be.
Sure. So Nala Membranes is a collaborator on our National Alliance for Water Innovation project related to electrospray processing of new membranes. We thought they'd be a great partner because a lot of these membrane companies that have developed water treatment technology have developed it around IP of a polymer material, not on the manufacturing process. And so I want to team up with companies that have made cool materials but are still reliant on legacy manufacturing technologies to make their membranes. Does it make sense to process a new material using a 60-year-old technology? Absolutely not. It doesn't. You can't optimize its material properties based on a casting line. And so Nala, Zwitterco, Via Separations, Membrion, these are great companies that do really cool material science. I want to help process them into more effective membranes, but they are not from my lab.
You talked a bit about resource recovery, especially ammonia and phosphorus. What are kind of challenges you're seeing to actually get those solutions to the market?
The challenge with capturing ammonia and phosphorus from wastewater are probably the offtake agreements. Who's going to buy them? And also what quality you can actually achieve. If I'm making a very low concentration ammonia product or a very, I would say, mixture of acids instead of just phosphoric acid, also hydrochloric and sulfuric, who's going to buy that? There's actually an interesting perspective. You might actually be able to use those as loss leaders because the benefit to the actual process is the ability to process more organics in an anaerobic digestion. If I can pull out the ammonia, I dialyze the digester, improve biological performance, I can intensify the performance by a factor of 6, making the same digester able to process 6 times more organic waste. That is the benefit because that will increase tipping fees by a factor of 6. That's why ARPA-E is so interested in this particular technology platform. USP Technologies developed the idea of intensified anaerobic digestion, and we've just made it better by actually recovering some value from the things they're pulling out. We should be able to generate revenue, but it might not necessarily be a super high quality product, but it doesn't have to be if you can sell it still and improve the performance of your overall system.
Sorry, building off of that, and like the economics aren't really on the nutrient recovery, it's the efficiency of the product, and it's a nice benefit. But what do you think needs to happen for it to become profitable, or in what type of industries the recovery itself not linked to the efficiencies that it creates?
It's a great question. I mean, if we started charging for carbon, it would be a pretty easy answer, but we don't. So like Haber-Bosch is horribly inefficient for making ammonia, but it's also very good at it. And it makes ammonia in large quantities, and we're not going to necessarily be able to displace Haber-Bosch, but we can displace a small portion of it to improve the overall climate impacts and life cycle benefits. I believe that in a system like that is being developed for our ARPA-E project, the economics are holistic. And so we're going to get better money at the tipping fee on the front end because we can process more organic waste. That's the big money. We're going to make more gas, which can then generate more electricity. And so Greater Lawrence Sanitary District, our partner, they do this up in Massachusetts, and they actually have a 0 electricity bill because they can process all of their organic waste and generate enough power to run their entire wastewater plant. $3 million a year of savings. So that's a huge opportunity for revenue if you can kick money back to the grid. And then on top of that, you're going to capture a little bit of value from these critical minerals, or in this case, nutrients that the Department of Energy has identified as being critical due to the possibility of supply chain risk.
So water is our first strategic initiative in ClimateHaven, and now you probably have a sense of why we decided that should be the case. Because Connecticut has so many wonderful centers doing work at the early stage commercialization, including access to facilities, but also helping startups really build the tech. So next we have Professor Lut Raskin, who will be presenting next, and followed by that, Professor John Fortner. Thank you.
Hello, everybody. My name is Lut Raskin. I'm a new professor here at Yale University. I moved here just a few months ago from the University of Michigan. So I'm really delighted to be here because it gives me an opportunity to meet some new people. Pretty much everybody's new here for me. So I'm going to give you a little bit of an overview of the research that I'm doing in my research group and touching on some future work that is moving to Yale. And I have framed this a little bit more basic than some of the previous presenters, so hopefully this is still helpful. But I have here a schematic of an engineered or an urban water cycle, and you see there's a lot of elements to it. And the previous presenters have actually talked about many of these elements. But the reason I have this up here is that I wanted to highlight that microorganisms like bacteria, for example, are really critical within this urban water cycle. We like maybe not to think about this, that there are microorganisms in our drinking water and that we use microbes to treat our water, but this is part of the urban water cycle, and I just wanted to highlight that with this schematic. In my research, we focus on various aspects of this engineered water cycle. One of them is drinking water treatment. And we focus again on the microbiology of things. We use microbes to improve treatment, biological treatment we call it, but we also think about reducing the risk of infection. So developing new technologies, helping utilities think about how can they reduce the risk of infections due to exposure to drinking water. And when we talk about microbes that are a concern in our drinking water, these are some of the types of organisms that we're talking about. We call them opportunistic pathogens because most people don't get sick from them, but if you have compromised immune systems, you may get sick from some of these organisms. And some of them may sound familiar. In this region, Legionella has been of concern, not necessarily due to drinking water, but we have these organisms in our drinking water. In some drinking water, we have relatively high levels of the lower organism there, the non-tuberculous mycobacteria. And that is the group of organisms that we have done most of our work with. And this is just kind of a general statistic. These types of organisms are present in 80% of our treated, disinfected tap water. Most of you don't need to be concerned about this, but if you have a compromised immune system, you could potentially get sick. And of course, the EPA is paying attention to this. So I'm highlighting there that the new contaminant candidate list that just came out in draft version lists 9 of these organisms. And so that tells us that perhaps these organisms are going to be regulated in the future, so we need to pay attention to how we treat our water to reduce the levels of these organisms. My team has worked collaboratively with utilities on problems like these non-tuberculous mycobacteria and on a lot of other topics. And here's just kind of a flavor of the types of projects that we have worked with utilities on. And as you can see, these projects are collaborative proposals that we write with the utilities that are then funded by organizations like the Water Research Foundation or the EPA. Rather than going into more detail on all of these, I wanted to just expose you to some topics of recent work to give you an idea of the kind of work that we can do working collaboratively with utilities. From this slide, you see that we've worked on a lot of different topics. So if you have more questions, let me know, and I'm happy to talk more about other topics. But this is an example of a question that came to us by the city of Ann Arbor. So Ann Arbor Water was required by the Michigan EPA to install a low-dose UV system to treat their water because there was concern that maybe they had some pathogens breaking through their treatment process. And these pathogens are called Cryptosporidium. So they installed this UV system, and then they came to us and say, well, what does this system do for our downstream water quality in the distribution system? Could there be benefits to reducing the levels of these non-tuberculous mycobacteria that we have in our water? So we set up our online flow cytometer at the utility, and we monitored during periods of operation with the system on and with the system off. We love working with utilities when we can do full-scale experiments. Sometimes that's possible, sometimes it's not, of course, because delivering water is always the highest priority. But in this case, we compared performance of the system with and without UV on. what I should say, maybe going back one slide, is that with this real-time flow cytometer system, you can measure total bacterial cell and you can measure the cells that are intact or alive. And what we observed is that the y-axis here gives you the concentration of the cells. This is a log scale. So you can see that the total cell count was very similar for these two periods that we monitored, but when we looked at the live cells, the intact cells, we saw a huge difference when UV was on. So this was very encouraging to the utility. This UV system is not just removing cryptosporidium, but it's also reducing the levels of bacteria in their downstream water. And so then we said, well, okay, general bacteria are present in your water, but what about those non-tuberculous mycobacteria? So we set up to do culture-based experiments to recover non-tuberculous mycobacteria from before the UV and after the UV. And you can see here in the y-axis, again, these are the colony-forming units, a measure of the concentration of these organisms in these different sampling locations. And you basically see there's no significant difference. So unfortunately, this UV didn't make a difference for non-tuberculous mycobacteria. So now we have to proceed and do some future work to help the utility think about this, and we are actually doing some experiments with them right now. But something that we're really excited about is thinking about the role of viruses. 1 minute left. Okay. The role of viruses in the control of these non-tuberculous mycobacteria. So phages or bacteriophages are viruses that infect bacteria. And the question is, can we use them to help control bacteria? We've done sampling from the water from the utility and recovered some of these non-tuberculous mycobacteria genomes and viruses. And we have indications that these organisms are present, organisms of concern based on this regulatory information that I shared with you. And we have some very preliminary data on these concentrations of organisms at different locations in the distribution system. And now we are starting to add to this levels of viruses. And we're seeing that the viruses don't necessarily match the levels of these non-tuberculous mycobacteria. So when we have low concentrations of bacteria, we have high levels of viruses, and vice versa. And so this suggests to us that we can do some future work with the utility to really explore these different directions. Maybe, can I take 1 more minute? I wanted to just briefly touch on another part of my research that's focused on that lower part of that urban water cycle. And so we are also looking, like Jeff is, on recovering resources from waste streams. And so here's my overview slide to give you a flavor for the types of products that we can produce using organic waste streams. And one technology that we have developed is a dynamic membrane bioreactor system, very different from the membranes that Jeff talked about. We have a mesh support that supports the development of biofilms and also serves as a filtration device. And we integrate these dynamic membranes in bioreactor systems, and then we run our studies to see how these systems can improve the yields, and we integrate these with other upgrade technologies to produce, for example, renewable natural gas. We have membrane separation systems to recover medium chain carboxylic acids. These are products that are much more valuable than the biogas that I mentioned earlier, and they can potentially be upgraded to sustainable aviation fuels. So these are additional technology developments that we're working on. We have a startup that's focusing on these anaerobic dynamic membrane bioreactors, Aquara Biosystems, there on my slide. And you can see that we collaborate with quite a few industry partners and with Argonne National Lab on these projects as well. So that just gives you a little bit of a flavor of the type of work I'm doing. I'm still transitioning to some extent. I still have some students at the University of Michigan finishing up their work. And here on the right-hand side, you see the team of people that are going to be out there at the end of the summer, so then we can really get going here at Yale with the continuation of this work. So thank you. Hopefully there's a little bit of time for questions.
Thank you very much. No one yet has touched on AMR and the role of AMR in wastewater. You almost did.
Uh-huh.
And are you doing anything in that area?
I've worked on and off on AMR. I am currently not working on it, and the reason for this is that I am honestly tired of monitoring AMR. What I would love to do is finding technologies that address the problem of AMR.
You almost did with the phages.
So the phage work is really new for us, and so we're going to continue that in the context of these non-tuberculous mycobacteria, many of which are antimicrobial resistant, by the way. But we might move back into that, but at this moment, I really would like to work on technologies that can address AMR, and otherwise I'm not going to touch that anymore.
Yeah, but the problem is it's the biggest single threat to humanity. And if we don't start addressing this at a very serious level in the wastewater environment, and the EU has now begun very significant measuring.
Right. I don't disagree with you. It is a serious threat. We recently, a couple of weeks ago, had a world-renowned expert on AMR visiting here at Yale, and I had this exact conversation with her, and it's like, instead of monitoring and hyping up the fact that we have a problem, let's work on technologies to address it. And she agreed, but even in her group, not much is going on, so I think we need kind of a reset in the research field to address this concern.
I invested about 6 years ago in the AMR company for measuring. We have a lot of applications, and we are able to help show applications which would change the risk factors. But
Okay.
And it has to act. You have to
Yeah,
act.
I would love to, maybe we can talk afterwards. I'd love to hear more about it.
Thanks so much.
Perfect. All right. So thanks for sticking around in this session. My name is John Fortner. I'm in the Department of Chemical and Environmental Engineering as well here. And my lab focuses on understanding materials, developing materials and those interfaces to tackle and solve some of the world's hardest problems in terms of environmental issues. And today I'd like to talk about one of our technologies that is very exciting. It's how to destroy these forever chemicals just using light and a novel new catalyst that we've developed. Is everyone here familiar with forever chemicals, PFAS? Of course, okay. So PFAS is an evolving landscape with regard to regulation and our understanding of impact. So today, we have a new regulation for PFOA and PFOS, these are the two chemicals here, PFOA on the left, PFOS on the right. And they have this saturated fluorine, carbon-fluorine backbone that makes them really difficult to treat. We have new regulations that will go into effect in 2029. They're asking for an extension. But we must treat drinking water down to 4 parts per trillion. It's an extremely low standard and a very difficult challenge to meet. With this, and we're doing this because there are associated health effects with PFAS. They estimate about $60 billion in PFAS-related health impacts here in the U.S. It seems like a lot, but we spend about $15.5 trillion overall on healthcare expenditures. It's about the same in the EU. And the hard part about this is these compounds are really difficult to treat in an effective way given this scale. The scale is enormous. For example, if it went into effect today, we have over 100 million people out of compliance estimated above that 4 parts per trillion. There was a recent study done in ES&T, Environmental Science and Technology, it's a journal. They estimate over 57,000 contaminated sites in the U.S. alone. A lot of these are industrial sites. 4,000 wastewater treatment plants are out of compliance or detectable PFAS, a lot of military sites, and a lot of airports. And this is because they use a lot of PFAS to make these really tough, effectively, firefighting foams that don't break down in high temperature. That's why they're really good. Then what happens when you train with all these foams, you spray it everywhere, and it goes into the groundwater, right, or drinking water with that. So the problem is enormous, and this is the global problem, too, with this. So we did a market analysis. This is pretty high-level market analysis for this, but given the regulations and the volume of the problem, it's big. All right, so industrial waste streams, you're looking at about a $30 billion market right? An accessible market, about a third of that. Overall water treatment would be over $100 billion estimated market for PFAS treatment alone to manage the upcoming deadline for the 2029 enforcement for PFOA and PFOS. So my lab has a stable of technologies with a lot of IP around it, thinking about how to treat PFAS in a number of different ways. And for the sake of time, I'd like to chat about a really exciting new technology that we just published in Nature Water, how to destroy PFAS in a way that's unique as it relates to the chemical mechanism of how it breaks down, and with that, the energy required for this, right? So we're going to harness light here to break down PFAS. And I can talk about some of the other technologies we have later on during the day. Most tech breaks down PFAS, so if you pick one of the fluorines off of PFOA, you've effectively treated it. It's no longer PFOA, right? And by this, the regulation, you've done your job. Now, have you? I don't know. There's liability with that. The biological mechanisms that make PFOA toxic, with or without that one fluorine, are probably about the same, right, in the future with this. Yeah? So those are going to be liabilities that must be dealt with if you incompletely treat PFAS. Yeah? And most technologies do that. They make shorter chain PFAS, which are actually more difficult to treat, right? And they don't effectively detoxify, right, the problem completely. Our technology is we've developed these materials that have a plasmonic aspect to them. They're quantum-sized catalysts, and when you shine light, you can actually have hydrated electrons effectively ejected from that interface, and they're really good at picking off these fluorines. So it looks something like this. And so the idea was, can you harness this completely to pick off every single fluorine from the backbone and completely detoxify, if you use that word pretty loosely here, the molecule itself with this. And so we've done just this. So our particles look like this on the left. This is a mesoporous silica particle, right? It has very high surface area, around 700 meters squared per gram. So 700 meters squared would fit in the palm of your hand in terms of surface area. And all those bright spots are quantum-sized palladium catalyst at very high loading rates. And when you add this catalyst to light, right, and you have PFAS on the left, right, as a function of time, you degrade both PFOS and PFOA. Now the question is, what are you degrading it to? And what we degrade to is completely stoichiometric release of the fluorine itself without breaking the carbon backbone. It is the holy grail of PFAS treatment, effectively, right, to remove all of this toxicity just with light at this interface at room temperature with no other inputs in the system. Where does it stack up in terms of technology? How do you go backwards? Traditionally, we would either store PFAS on activated carbon. That's how water treatments do it today for the most part. Or you do something like reverse osmosis. Even that has problems. So you have toxicity removal here as a function of energy demand for this quadrant. You can also burn PFAS, right? But it takes a lot of energy to break that carbon-fluorine bond. That's why they use them in these firefighting foams, right? There's been a lot of work in the last 5 years with startups and new technologies to enter this space, to address this problem. They have the same problem with this defluorination energy demand trade-off, right? And there's a lot out here, and I'll get to this in a minute. But ours is different because we have basically a low energy demand, just light itself. You can use UV or in some cases even sunlight, and we get complete defluorination. So we're breaking this paradigm that's sort of been the problem for so many folks doing this. Did a fairly large market analysis of tech in general. And we stand at or near the top with regard to sort of treatment efficiency, defluorination, as it relates to energy requirements for this process. And our idea here, we have IP around all of this, is to basically, we have to commercialize this technology to address the problem, period. If you want to reach the volumes that are required, it has to go through some type of commercialization process. And we see a couple of different ways to do that, but first thinking about just industrial waste streams that are so concentrated, right? You could effectively be on site to address these before they reach the environment and sort of go from there. But there's already commercial reactors that we can plug and play our catalyst into and see where that is. And we just recently received amazing amount of support from Yale Planetary Solutions and the Impact Accelerator to do just this. So it's a 2-year project focused on going from the lab to commercialization.